Oh, good. My class is about to start and Allison walked out.
Where is she?
In the garage.
That's 30 pounds in front of the door.
Okay.
All right, good morning, ladies. So let's start off kind of with a quick recap of what we talked about on Friday. And I already started recording, so Katie doesn't have to yell at me, so that will be good. Good. So Friday recap. So we started the new portion, which involves then what we're going to stay with for the remaining of the semester, which is then electricity and magnetism. So we're going to start off with electricity first. And right now we're mostly looking at what's known as electrostatics. So electrostatics. And I'll talk more about what that means. Basically, it just means that non-moving electric fields, but we'll come back to that. So basically, we said is that now all material, so all matter has now a new intrinsic property. That new intrinsic property is what we call charge. So all matter has some sort of charge, which is assigned to it by some reason. And then we can also get forces which occur because of these charges. So if I had, say, 2 point charges, which here I have one charge Q1 and one charge Q2 separated by some distance from center to center of those charges by a distance of r, what Coulomb's law tells us then is that the electric force that these guys feel is equal to K, or K is a new K, so we have now 4 Ks. All right. So K number 1 is what? Boltzmann's constant. K number 2 is the spring constant. K number 3 is the wave number. And now K number 4 is the, let's call it the electric constant.
The cat is trying to claw its way out of my room. Can someone come get it? I'm so
Adrian,
sorry.
you're not muted.
So
Just to let you know. Okay. So anyways, so basically we have 40 K values now. So we have to keep track of which K value that we're actually talking about most of the time. So we just have to make sure that we know which K it is. So that'll come from context of what we're basically asking in the question, but just note that we have 4 different K values, so we do have to be a little careful which K value we're talking about. So again, this is K times Q1 times Q2 divided by the distance r squared, or we're also going to write this as 1 over 4 pi epsilon naught, which means that K is also equal to 1 over 4 pi epsilon naught times K1 or Q1 Q2 divided by r squared, where epsilon naught is what's known as the permittivity of free space. We're going to use this quantity a lot, as you'll see in the future, so I'm just going to write it down. So it's defined as 1 over 4 pi times K, which has a value of 8.85 times 10 to the minus 12 Coulomb squared per Newton meter squared, where K itself has a quantity of 9 times 10 to the 9th Newton meter squared per Coulomb squared. Now, electrical force, also known as the Coulomb's law, is a little more complicated, unlike the gravitational force. Remember that the gravitational force has exactly the same structure, which was Gm1 m2 divided by r squared, where if this guy had a mass m1 and this guy has a mass of m2. But the gravitational force is always an attractive force. This guy is always attractive. Now, when it comes to the electrical force, or Coulomb's law, this is a little more complicated because now there's 2 different types of forces I can have. We can either have an attractive force like gravitational, or we can have a repulsive force. So it turns out that when I have unlike charges, so for example, let me use blue one here. Let's say Q1 is positive and Q2 is negative. This would result in an attractive force. So basically meaning that Q1 is going to be attracted to Q2 along the line that connects the 2 of them together. So Q1 will be pulled towards Q2. Simultaneously, Q2 will be pulled towards Q1. These satisfy Newton's third law. So it satisfies Newton's third law. But if I had like charges, so for example, if they both were positive charges instead, this would have resulted itself in a repulsive force. So in this case, Q1 would be repelled from Q2. Simultaneously, Q2 would be repelled from Q1, where the magnitudes of these forces would be the same. They're just in opposite direction. So remember, Newton's third law says that the force and the two are the same magnitude, just opposite in direction. So this is what Newton's third law tells us. Good. So this is Coulomb's law. So again, all matter has this extra property, what we call an intrinsic quantity. That intrinsic quantity is charge. That charge then can actually create a new type of force, which is this electric force. Now, one thing to note that I didn't talk about last time, it turns out that when I compare Coulomb's force here to the gravitational force, Coulomb's force is much, much, much stronger. So Coulomb's force will always be dominant over gravitational force. So anytime I have electric charges and masses for these things to gravitationally attract each other. So like here, if these guys both have positive charges, the electric force, which is going to repel these guys, is much more dominant than the gravitational force trying to attract these guys. So which is always going to be true is that the electric force is much, much bigger than the gravitational force. Gravitational force is ridiculously weak. It's the weakest force that we have. Okay. Which is actually kind of funny because gravity wins at the end of the day all the time. So even if I have electrical forces, gravity will eventually prevail, which is why we get things like black holes and supernova and pulsars and all that kind of good stuff. So great. That was a side note. Let's talk about an example. So we use this then to talk about a couple of examples. So this was the second example that we didn't finish. When the Gestapo was coming down the hall trying to get into the room. So anyways, here we go. So here we have two charges. The first one, Q1, has a charge of 8 times Q, whatever Q is. Q2, which is some distance away, where'd it go? Here it is, has a charge of minus 3Q, and is some distance L away from the origin, where Q1 is at the origin. Okay. Actually, no, we're bringing out the wrong problem. There we go. Yeah, minus 3. Okay. Now, what we want to know is where can we put a third charge, Q3, which has a charge of 5 times Q, so that that one is in equilibrium, which basically means that it's going to have what? 0 net force acting on this guy. So let's talk about that. So this one has a charge of negative 3Q. And what I want to do is take another charge here, Q3, which has a charge of 5Q. And I want to put this into the configuration somewhere so that the net force on Q3 is equal to 0. Now, we talked about it last time. What that means then is we want the net force, which is then the force between 3 and 1, plus the force between 3 and 2 to be equal to 0. That's what this thing means. So this is what we call superposition. So again, superposition just says that the total force on some charged particle, let's say here 3, is then simply equal to the vector sum of all the individual forces from all the pairs that this thing has acting on it. Good. So let's kind of recap what we talked about last time. So let's break this up into 3 zones and try to figure out which zone this thing is allowed to go into. So the first zone, let's look at zone 1 here. So let's say I put Q3 here. So the question is, could I put Q3 at this location so that it has 0 force acting on it? And I think it was Katie rightfully said that, no, we can't put it here. And the reason for that is that, what? If we think about Coulomb's law again, where Coulomb's law says that this is K times the first charge, right? So in this case, this is going to be Q1 times Q3 divided by R squared. So it's going to be the force on 3 by 1. Then here, this has a very large magnitude, right? So this is 5 times Q times 8 times Q. So it has a large numerator. And this distance is very small. So in this case, it has a small numerator or denominator, which makes this overall a very large number. So this is going to result itself in a repulsive force which pushes in this direction. So this is going to be F31. Simultaneously, we know that this is a negative, which means it's going to be an attractive force. But since Q2 is smaller than Q1, then that means the numerator is not going to be as big. And since this distance is much greater, that means it also has a larger denominator, which means it's going to be a much smaller number. So ultimately, this is going to result in an attractive force, but it's a very small attractive force, which is then F32, which means the total force on this thing is going to result in a force in this direction. So this is going to be F3. So basically, no matter where I put this thing in zone 1, F31 will always be bigger than F32, which means it's going to result in a repulsive force to the left. So nothing over here can happen. Right? I can't put it over there because it's not ever going to be in static equilibrium. Now let's think about zone 2. So let's say I put it here in zone 2. Well, in zone 2, what I know is that these are both positive charges, so that results itself in a repulsive force. So you're going to have F31 in this direction. But this is a negative charge, which means that's an attractive force, so that's going to pull it also in this direction. So this is going to be F32. So overall, these two forces point in exactly the same direction. So in this case, the total force will be a force which is pulling it towards Q2. So F3 in this case will be a single force which pulls it in this direction, which tells us that we can't put it in zone 2 either, because zone 2 will result itself in a force which only pulls to the right, pulling it to Q2. So finally, the only place we can put it then is going to be somewhere out here. So here, if I put it Q3 here, well, in this case, I get an attractive force between Q1 and repulsive force between Q1 and Q3. So it's going to point in this direction. So this is going to be F31. But I get an attractive force between 1 and 2, which is going to pull in this direction. So this is going to be F32. But again, here, even though the numerator is greater between 1 and 3, but the distance is bigger, which means the denominator is going to be bigger, which is going to bring down the overall number. So ultimately, what will happen then is I can find a position here, which is going to allow these two things to be equal to each other in magnitude, opposite direction, so I can have a static equilibrium in this case. So the only place I can put this thing is in zone 3. Good. Now, let's define this distance here from the origin to the location, and I put this as x. Okay. So Coulomb then says then that the force on 3, which is equal to 0, is then equal to F31, which points in a positive x direction, minus then F32, which points in the negative x direction. So that's where this minus sign comes from. So the minus sign is from the negative x direction. So this tells me then that what? The magnitude of F31 just must be equal to the magnitude of F32. Now let's use Coulomb's law. So this says then now we have K times Q3 times Q1 divided by, well, the distance between 1 and 3 is just x. So this is divided by x squared, is then equal to K times Q3 times Q2 divided by that distance. Well, that distance is going to be what? This total distance of x minus then the distance of L. Because if I go, what? Out to x, and then come back L, then that's going to be this distance here, which is the distance between 3 and 2. So this is going to be x minus L quantities squared. Okay? Now notice on the left-hand side, I have a K, so I can cancel that out because I have one on the right. I also have a Q3, so I can cancel those out as well. So we go to the next page. So what that says then is I have simply Q1 divided by x squared must be equal to Q2 divided by x minus L squared. Okay. It's okay? Now from here, what I want is the x. So let's go ahead and take a square root of both sides to get rid of that squared. So this now says I have a square root of Q1 divided by x is then equal to, now here we have to be a little bit careful because we had written down Q, but we really mean here is absolute value of Q2. Because remember, Q2 is actually negative. But if we go back to our previous page, when we took this negative sign into account, we were taking into account that it was a negative pulling it backwards, right? So once I put this guy in here, what I really mean is that this is absolute value of Q2. So I'm only using the value of it instead. Square root then of the absolute value of Q2 divided by x minus L. So finally what we want is simply x. So let's cross multiply. So this is going to give me x minus L times the square root of Q1 is equal to the square root of absolute value of Q2 times x. Distribute, and then we're going to subtract. So finally, this is going to give me what? So we'll do it in steps. So it's going to be the square root of Q1 times x minus the square root of Q1 times L is then equal to the square root of the absolute value of Q2. Sounds like my daughter is awake, times x. So I'm going to add this term to this side, subtract this term to this side. So finally, what I'm going to get is the square root of Q1 minus the square root of the absolute value of Q2, all times x, is equal to the square root of Q1 times L. Or finally, x then is equal to the square root of Q1 times L divided by the square root of Q1 minus the square root of the absolute value of Q2. Plug in my numbers. What I find in this case, if I remember correctly, is somewhere around 2.58. Great. So this is then 2.58 times L. So basically what this says is to find the location of the static equilibrium. We go back to our picture, it's going to be 2.58 times the length of L. So if this is L, 2L would be about here, 2.5 would be about this location. So this is around where we would have to put in Q3. Now notice something that's kind of weird about the solution, but the solution here doesn't depend on the value of Q3. So what does that mean? So what that means is, first of all, it doesn't matter if Q3 is 5 times the charge Q, or if it's 6 times the charge Q, or it's 100 times the charge Q, that distance is still the same. And the other thing it says is it doesn't matter if it's positive or negative. So it doesn't matter if it's negative 5Q or positive 5Q, the position is exactly still the same. The only thing that's going to be different is if it was negative, over here, this force, instead of being to the left, would be to the right. And in here, this force would be to the left instead of to the right, but this location would still be exactly the same. And again, the size of it doesn't matter either, so it doesn't matter if it's 100 or 1,000 times Q or 1 times Q. The position is also the same because of the structure of Coulomb's law. So since this is the product of the charge is the same, which means that the numerators just grow the same rate, right? So the numerator of the force between these two charges grows exactly the same way that this one does, which makes it irrelevant of the size of then Q3. So it's actually kind of interesting about this is it doesn't depend anything on Q3. That location is still the same. The only thing it depends on is the size of Q1 and Q2, which is actually kind of interesting. So this is then Coulomb's law. Okay. Okay? So this is Coulomb's law. So again, Coulomb's law is the force between two charged particles that are discrete charged particles. But let's make some notes about this guy. So let's make some notes about Coulomb's law. And first off, number one, it satisfies Newton's third law, meaning that the size of the force is exactly the same. They just point opposite directions. And the second thing we want to point out is that these are indirect or non-contact forces. So these are indirect or non-contact forces. There we go, forces. Which basically means that, again, these things are spatially separated, and I have a force which is acting between two objects which are spatially separated. Now, the idea of non-contact forces really bothered physicists for a long time. Okay? This is what was called spooky action at a distance. Spooky action at a distance. So why you would have forces between two objects just kind of puzzled physicists for a very long time. This was the same thing for gravitational forces. So why would you have some sort of force between two things which are separated when they're not in direct contact with each other? So the question became, so how does this charge here, Q1, know about this charge, Q2? How does it know that there should be these charges and that these guys should actually feel a charge and feel a force? Because they're indirect and non-contact forces. So for about at least 100 years, this really bothered physicists. They didn't really know what to do with it. They didn't know how to treat it. Until eventually, a British physicist by the name of Michael Faraday gave a resolution to this. So he gave a resolution. And we're going to see his name several times. So his resolution to this was that what's actually happening is that there exists a field called the electric field, which is generated by the presence of charge. The force is the result of the interaction between this field and the charge. So this was his resolution. So what he decided and what he said, which turns out to actually be true, was that the presence of charge creates something which is called the electric field. This electric field then permeates through all space. And then what's really happening here is that Q1 is creating an electric field, and then Q2 is interacting with that electric field, which is generated by Q1. So Q2 knows about the presence of Q1 because of the electric field, which is generated by Q1. So it's the interaction between the field from Q1 and the charge Q2, which generates in the force. But simultaneously, since Q2 has an electric charge, he creates his own electric field, and then Q1 is interacting with the electric field from Q2, which then generates the force on Q1. Okay. So this is the resolution of this spooky action at a distance. So it's not that they're interacting indirectly, but they're interacting with the field which is generated by each one. So this is also true for gravitational. So the Earth itself has a gravitational field. The moon is interacting with the gravitational field of the Earth, so the moon knows to stay in orbit around the Earth due to the interaction with this field. So we're going to have to take some leaps of faith at this point. So now we're going to talk a lot about this electric field. So the first thing we want to know is, okay, so I've used this term field a lot. What the hell is a field? So this is the first question we need to ask ourselves. So the first thing is, what is a field? So a field is a quantity which has a value at all locations in space. So this is a field. So a field is a quantity which has a value at all locations in space. Now, it turns out there are, for our purposes, two types of fields. So there are two types of fields. The first type is what's known as a scalar field. And the second type is what's known as a vector field. So what's the difference? Well, a scalar field is only a quantity which has a value at all locations in space, just like a regular scalar. So remember, a scalar is something which has no directional property to it, it only has a value. So the scalar field then only has a value at all locations in space. And I'll give you some examples of what this means. A vector field is something which has both a value and a direction at all locations in space. So this has a value and a direction at all locations in space. So, what are some examples of this? So, a good example of a scalar field is a temperature map. So let's say here's my temperature map. Okay, so let me make this a little bigger. Hopefully it doesn't break anything. There we go. So this is a temperature map. So what this thing says is, okay, here's the US, and all of these different colors correspond to different temperatures throughout the entire US. I have no idea when this is from, but we'll just go with it, okay? So this is a scalar field. So what this is saying is that at every location in space, which in this case, my space is the continental US, there is a value of the temperature at every location in this space. So this is a scalar field. So this is the temperature field, which is a scalar field, which says that if I was looking at Evansville, which is about down here, then at Evansville, which has a location in the space, right, which in this case would be given by its latitude and its longitude, it has this particular amount of temperature, which is somewhere between 30 and 32 degrees Celsius. So this is what? Summertime. Or if I was thinking about somewhere here, so this is probably what? It's probably around Houston, I think. So if this was Houston, then Houston has, again, its longitude and its latitude, which means it has a location in space. At that location, its temperature is somewhere between 32 or 34 and 38. Or New York City, somewhere about down here. So it has its location, has a temperature between 28 and 30, and et cetera. Right? This is about Tampa Bay, Florida, somewhere about here. So that's about 32 to 34. So this is an example of a scalar field. So a scalar field, again, is at every location in space. So once I know the particular point that I'm looking at, so I know its XY coordinates or its latitude and its longitude, then at that point, there is a given value of the field at that space. So this is a particular scalar field. A vector field would be like a wind map. So if I was looking at something like this. So this is the surface wind speed and the streamlines. So this is also, again, continental US, a little bit of South America with Canada on here. But here, this would be a vector field. So here, again, at every location in space, there is a given value. So again, if I was looking at, let's say down here, New York City, in this case, its value would correspond to around what? I'm trying to determine what that color is. I don't know, let's say about 30. So it's about 30 knots, and its direction is what? A little bit west of north, right? So in this case, it has a particular value, but it also has a direction. So each one of these arrows tells me the direction of the field at that given location. So again, if I was looking at Evansville and here, its direction would be direction tangent to this curve. So again, it would have around 30 knots, but then pointing off somewhere about what? South of east in this case. So these are good examples of fields. So again, a scalar field is a field which has a value at every location in space, but then a vector field is a field which has both a direction and a value at every location in space. So once I know the location of space, I know exactly the magnitude of it, and I can determine exactly its direction. So these are fields. So what Faraday was saying was that there exists this field, again called the electric field, which has a value at every location in space, and then it's the value of that field interacting with the charge, which then creates the force. But to make it a little more complicated, it has a vector component to it as well, so the electric field is actually a vector field. So let's talk about that. So in this case, we know that the electric field is a vector field. So how do we determine the electric field? Well, the electric field then is defined as the limit as Q goes to 0 of the force divided by the charge. Okay. So let's talk about what that means. So what this means is, let's say I have some region of space. So here's my space. Okay. Now what I'm going to do is I'm going to take something called a test charge, Q, and I'm going to drop it in my space. So this is Q. Q here is what's known as a test charge. And then basically what we're going to do is we're just going to sit back and watch how Q moves. Okay. So basically what I'm going to do is I'm going to watch and see Q maybe follows this particular path through the space. And at different locations, we can then find the force. So let's say at this point, it has a force pointing off in this direction. At this point, it has a force pointing in this direction. And at this point, it has a force pointing off in this direction, and etc. Okay, so overall, the path is following this particular path in this direction. But at these locations, I'm measuring the force, and this is the force that I find at those locations. Okay. So what this is saying then is that what? The electric field at every single one of these points is then equal to the force divided by this charge. So what this says then is that at this point here then, my electric field then points in exactly the same direction as the force, but it's much bigger than the size of the force because the charge is small. And so at this point, my electric field points this way. At this point, my electric field then points this way. And then at this point, my electric field points, say, this way. Okay. So what this says then is if I want to know what the electric field looks like throughout the entire space, we're simply going to drop this point charge then into the space, watch how it moves, and then measure the direction and the magnitude of the force at different locations along its path. Then by knowing the direction of the force and the magnitude of the force at those different locations, we can then determine exactly what the electric field lines look like. So what this says then is the electric field lines point in the same direction as the force, because we're assuming that here Q is positive. If Q is negative, then it would just be in the opposite direction. And then the magnitude of the force, or the magnitude of the electric field, then is the magnitude of the force divided by the charge. So this thing has units of what are known as newtons per coulomb. So this is the units of the electric field. Okay. Then if I drop my test charge in, say at a different location here, Q, we would do the same thing. So let's say this might follow this particular path here. So again, we just measure the force at different locations. And then we map out the electric field that way. So the way we map out the electric field is, again, by simply taking the charge, the test charge, throwing it into the electric field configuration, watch the force which happens on it due to this electric field, and then we can map out exactly what the electric field looks like. Okay. So again, what's happening is that the charge itself is interacting with the electric field, which is generating the force. Okay. Now, why do we take the limit that Q goes to 0? Well, we do that because what we want is for this thing to be exactly this test charge, which means that when we put in the charge, we don't want it to change the configuration of the electric field. So if we put in a much bigger charge, what'll happen then is it'll cause the charges which are creating this electric field to move. As those charges move, it then destroys the original electric field configuration, which is not what we want, right? We want to know what is that electric field configuration, which is why we're using this test charge. So this is in here to ensure that our field configuration does not change. Does not change. In fancy terms, this is what we call back react. So we don't want it to back react onto the configuration to change that configuration. Okay. So this is how we map out and determine the electric field. So again, we assume that since there's presence of charge, that presence of charge creates an electric field. And if we want to know what does the overall field look like, we drop in this test charge, watch how it moves, and then from there we can map out exactly what this electric field looks like. But again, it's a field. It's an electric field. So the electric field, again, has a value at every location in space, and it has a direction. Okay? So there are two quantities that show up with this. Okay? So going back to a question Callie asked me before about the exams, this is one of the reasons why this exam becomes more difficult, is because now we have to start thinking about reality in terms of fields. Okay? So fields now exist. So we have to come to terms with this idea of a field, that fields permeate all space, they have a value, and they have a direction everywhere. Okay? This is also going to be true about magnetic fields when we talk about magnetic fields. So basically, everything we're going to talk about from here on out is dealing with primarily fields. Okay? So we have to take kind of a leap of faith and kind of get used to this idea of fields. Okay? So your primary job over the next couple of days is try to come to terms with fields. Okay? Good. So how do we visualize electric fields? So let's talk about visualizing electric fields. So electric fields we're going to write as an E with a vector sign over top. So this is our electric fields. So how do we visualize these things? Well, basically, what we do is we assume that, again, a charge is what's creating the electric field. So if I have a positive charge, what we think about is that the positive charge is a source of electric fields. So what happens then is we create electric field lines radiating out in all directions away from this source of electric fields, which is then the positive charge. Okay. So basically, positive charges act as the source of electric fields. Now, even though I'm drawing this in a two-dimensional sense, we have to think about this in 3 dimensions, which means this points radially in all directions. So this is actually creating a sphere. So this is creating a sphere. Okay. So this is spherical. Now, simultaneously, a negative charge we can think about then as a sink, right? So this is your sink, the drain, where all the electric field lines are going. So what happens in this case then is that the electric field lines terminate on negative charges. So what happens here is that all the electric field lines point radially inward towards this negative charge. Okay. So these act as sinks. And again, this is 3-dimensional, which means this is also spherical. This creates a sphere. So basically, what we can do then is to visualize the electric field, what we have to keep in mind is that electric field lines start on positive charges and end on negative charges. So if I had, say, a dipole sitting in my space, which is a positive charge with a negative charge, so let's say here's a dipole, so I have a positive charge with a negative charge. What would have to be true then is that all of my electric field lines would have to originate from the positive charge. So I'd have to have something that looks like this. But they have to simultaneously end on all of the negative charges. So I would simply start off drawing this way. Okay. Then what I would do is simply connect these lines together. Okay. So my electric field then in this configuration, well, I would attach this line to this line. Say attach this line to this line. This one I might attach to this one. This one I would attach to him. This one would do something like this. Let's attach it to this guy. And this one would go off something like that. Okay. So this is our electric field. So in this case, our electric field would be attaching these lines together to then create my overall electric field. Okay. Well, this is one way we to visualize. Now, the strength of the electric field then depends on the density of the electric field lines, which basically means that the more dense the electric field lines are, so more dense equals a greater field, a greater electric field. So when I draw this, the greater the amount of charge I have, then the more electric field lines I would draw, so it has a denser amount of electric field lines, which then equals a greater strength of electric field. Let's do another example. So let's put two positive charges. So let me put a positive charge here and a positive charge here. So what would this space look like? So again, what I know is that electric field lines are radiating out everywhere away from the positive charge. Do the same thing here. So positive, 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 positive. So in this case, since I have no sinks, what would have to be true then is what? These lines can't cross each other, and these lines will not terminate on this one, but they have to actually diverge away from each other. So what happened in this case then is these lines would come out, but they would find the other electric field lines and then diverge away from each other. So these would actually diverge this way. This might go like this, and then this one would do that. Do something like this, like that. So this would be my electric field configuration, which means somewhere in the middle here, I could actually have the total electric field equal to 0. Okay. So basically what this means is that electric field lines can't cross. What actually happens is when I have electric field lines that are going to cross each other, they superimpose on top of each other just like waves and forces, and then create an overall electric field at that point. So electric field lines can't cross. They superimpose to generate a net electric field. Okay. And again, since they have vectorial quantities to them, if they point in opposite directions, they will cancel each other to then create 0 amount of field, like at this particular location. So one more charge configuration I want to draw for you is something we're going to see kind of a lot, and this is what's known as a infinite sheet of charge. Charge. Okay. So an infinite sheet of charge. So let's say here's my sheet of charge. I'm going to draw it from an angle. Okay. So that this is extending in this direction to infinity, in this direction to infinity, in this direction to infinity, in this direction also to infinity. So this is kind of an angle view. And then if I draw just simply a side view, let's say here's my side view. So let's talk about this electric field. So imagine what we usually do is we imagine that this thing is actually made up of a bunch of charges. So let's say here's all my charges, which are creating this sheet of charge. Okay. And for funsies, let's just take all of these to be positive charges. So let's think about the electric field lines from each one. So here, since it's positive charge, I have electric field lines which point radially away in all directions. So these are my electric field lines for this one. Pointing off in this direction, and this direction. And let's take another charge, let's say this one, and draw some electric field lines. So I have an electric field line here, electric field line from here, one here, one here, here, and here. So let's think about what's actually happening. So what's happening here is that what? Here, if I look at, say, this field line here, so let me draw which one I'm looking at. Let's do it yellow. So if I look at this field line here and this field line here, so notice what's happening is I have one pointing in this direction, one pointing in this direction. Now, if I say that both of these charges have exactly the same amount of charge, what this means then is that this electric field here has the same magnitude as this electric field here. But what's happening then is that the horizontal pieces point in opposite directions, which means if I vector sum the horizontal pieces, they're going to go away, right? So here, if I think about this thing being broken up into the vertical piece plus the horizontal piece, so here I have one horizontal piece pushing this direction, one horizontal piece in this direction. So the vector sum between this guy and this guy are actually going to cancel, which means I'm left with only the two vertical pieces. So basically what happens in this scenario is all the horizontal pieces cancel, which means the total electric field then is only going to point perpendicular to the surface. So in this case, I get electric field lines which only point perpendicular to the surface. So that means here, if I'm looking at this angle, my electric field then is only going to point upward, or in this case, straight downward. So this is my electric field. So for an infinite sheet of charge, then the electric field is perpendicular to the surface. And what's also interesting in this case is it turns out that the electric field above an infinite sheet of charge doesn't depend on the distance at which I am above the sheet. It's simply a magnitude the entire time. So the electric field is perpendicular to the surface, but doesn't depend on the distance. So it actually turns out that the magnitude of the electric field is actually a constant, which is given by sigma divided by 2 epsilon naught. Okay. Where sigma here is equal to the charge per area. So this is what we'd call the surface charge density. Surface charge density. So this thing has units of coulombs per meter squared. So all that means is what? This thing has a total amount of charge of sigma, which is the surface charge density, which means that if I want to know the amount of charge, I just go in and I grab an area, I measure the size of that area, and that's the amount of charge I have in that area. Okay, so this is sigma. Now from here, we can create those parallel plates that we talked about in lab yesterday. So in this case, we can look at the electric field from parallel plates. So let's say I have one parallel plate here, another parallel plate here, where this one is, say, positively charged. This one is negatively charged. So what we now know is that the negative one has electric field lines which terminate onto him, pointing in this direction. This one has them pointing in this direction. Okay. The positive one has electric field lines which radiate positively away. So let's draw those. Now, let's say this one has a charge of Q, this one has a charge of minus Q. So what happens in this case then is what? Well, if I extend the green lines all the way out to beyond this plate here, what you notice is that the electric field lines from the negative plate point downward, but the electric field lines from the positive plate point upward. Now, since these two have the same amount of charge, that means this electric field magnitude here is the same as this electric field magnitude here, which actually means that the total electric field outside of the plate is equal to 0 on both sides. The total electric field then on the inside is simply equal to twice the electric field of a sheet, which then is simply going to be equal to sigma divided by epsilon naught. So what actually happens in a parallel plate capacitor is that the electric field inside is simply a constant, and it points particularly from the positive plate to the negative plate. So if this was my positive, this is my negative, then my electric field inside the parallel plates only point in straight lines directly from the positive plate to the negative plate, which has a value of sigma divided by epsilon naught. Now, this is something else we're going to use a lot. So we'll use this often. So I'm bringing it up now, and then we'll use it a bunch later. Everyone's okay? So the next thing we want to talk about then is, okay, so now that we know the electric field is defined as the force per unit charge, how do we then determine the electric field of a point charge? So let's look at the electric field of a point charge. So let's say here's the point charge of interest. I'm going to call this capital Q. And let's put our test charge somewhere here. So this is little q. And let's say this is positively charged, this is also positively charged, so we know the force then points off in this direction. So this is my force. We also know by Coulomb's law, the magnitude of this force then is equal to kq times q divided by r squared, where r again is the distance between the center to center. So this is r. Well, the electric field then is going to be equal to the force per unit charge, which is the test charge, which is then going to be equal to k times q divided by q times r squared, which is then simply equal to k times q divided by r squared. So what this tells us then is that the electric field of a point charge is then equal to k times the charge of the point charge divided by the distance r squared I am away, pointing in the radial direction. So all this means then is if I was looking at this point here, then the electric field points in exactly the same direction as the force, but is different by the fact that now I'm just dividing by that charge of q. Okay. So if I was looking at this point here, in this case, then the electric field would point down in this direction. So this would be my electric field. If I was looking at this point, electric field then would point here, again, along the line that connects center to center to where that charge would be. And then here, the electric field. Okay. So in a way, you can think about the electric field as the force that a charged particle would feel if I put it at that location. So this is what the electric field basically tells you. So the electric field exists regardless if another charge exists there or not. So the electric field is telling me is if I put a charge there at that location, how much force would that charged particle actually feel at that location? So this is what we call the electric field. Okay. Some of these things. This one, good. Now, one other thing to talk about electric fields is since the force satisfies the superposition principle, then the electric field does as well. Since the electric field is defined from force, so what this means then is what? If I had a bunch of point charges sitting around in my space, so let's say I have a point charge here, so let's call that Q1, another point charge here, Q2, another charge here, Q3, and I wanted to know at this point here, let's call that point P, what is the value of the electric field at point P? This is what I want to know. Well, what this says then is that the value of the electric field at point P is simply equal to the value of the electric field from particle 1 at point P plus the value of the electric field at point P from charge 2 plus the value from charge 3 at that point. Okay. So let's say, I don't know, for funsies, this is positive charge, and negative charge. So in this case, I would have what? E1 would point in this direction, because that's a negative charge. It would point towards negative charge. Electric field 2 would point in this direction, because it's positive, so it points away. 3 also points away, so 3 is going to point, say, something like this. So this is E3. So the total electric field at that point in space then is simply the vector sum of all of these electric fields. So this would be my electric field at point P. So the total electric field at any point in space then is equal to the vector sum of all of the electric fields at that particular point. So that's this guy. So let's use this and let's do a couple examples. So the first example is we're going to refer back to this diagram. So this was one of the ones we looked at on Friday. So it says refer to the charge distribution from the previous example. See this guy below, except now we're going to ignore charge Q3. So basically I'm going to get rid of Q3, so we only have Q1 and Q2. So we want to know then is what is the electric field at point P or A, whatever you want to call it, which is the location of charge Q3. So what I want to know then is at this location here, what is the value of the electric field at that point? So this is what we want to know. So let's redraw. So basically I have one charge here, I have another charge here. So remember, this is Q1, this is Q2. And what I want to know is at this location here, this is my point P, what is the value of the electric field at point P? So this is what I want to know. So let's call this our y direction. So here's our y direction. Again, we know this was 30 centimeters. That bottom one is what, 52 centimeters? So this is 52 centimeters, which makes this distance across here 60 centimeters. And this angle 30 degrees. And Q2 we know was how much? 50 and 86. Okay, so this was 50 microcoulombs, and then this was minus 86 microcoulombs. Make sure I got all the right things on here. Yeah, okay. So again, what we want to know is what is the electric field at that point? So first thing we're going to do is exactly the same thing we did with forces, which are draw our vectors. Okay, so here we're going to draw our electric field vectors. So first things first is from Q1, we know Q1 is a negative charge, which means that the electric field has to point radially towards Q1. So in this case, it's going to point down in this direction. So this is going to be electric field E1. Q2 is a positive charge, so we know that the positive has to have electric field lines which point radially away. So E2 is going to point radially away from Q2, which is going to point off in this direction. Then the total electric field is going to be the vector sum of these two, so this will be my total electric field. So this will be EP. Okay. So we're going to do what we did last time, which is we're going to move our coordinate system to this location, the location of the point. So I'm going to call this the x-axis and this the y-axis, so that this angle here is going to be the angle of the electric field. And then this angle in here, again, is going to be 30 degrees. Okay? So let me redraw it a little bit bigger down here. So again, this is E2. This is E1. X. Y. And this is theta, which is the 30 degrees. Okay. So what this says then is that the total electric field at point P is simply equal to the electric field from the first charge plus then the electric field from the second charge. Okay. Now, as we can see here, as I had drawn, the total electric field is going to be two-dimensional. Right? So it's going to point off something like this. So in this case, we can root this into components. So we're going to look at the x portion of the electric field at that location, and then also look at the y component of that total field at that location. Good. Now from our diagram, we can see then that the only field which points in the x direction is that from E1. So this is going to be the x component of E1. And then the x component of E1, is that going to be a sine or a cosine? According to that angle. What do you think?
Cosine.
A cosine, good. So this is going to be E1 times cosine of the angle. Now let's use our formula from the other page. So this becomes K times Q1 divided by the distance, where the distance in this case is going to be this distance. So that's going to be our 60 centimeters or 0.6 meters, quantity squared times cosine of 30 degrees. Move this one down a little bit. Now the y component, it's going to be a little more complicated. So now we have all of E2 pointing in the y direction. So it's going to be E2 minus, because it points in the negative y direction, times E1 times the y portion, which is then going to be E2 minus E1 times sine of the angle, since the other one was cosine, so this one has to be sine. So this is now going to be K times Q2 divided by that distance, which is 0.3 meters squared, minus then K times Q1, where again, this is the absolute value of Q1, divided by that distance, 0.6 quantity squared, times sine of 30 degrees. Okay, so let's plug in the numbers. What we get in each one of these cases is once I find it. Okay, so in the x direction, that works out to be about 1.86 times 10 to the 6th newtons per coulomb. And then in the y direction, this works out to be 3.93 times 10 to the 6th newtons per coulomb. And then the angle, theta e, then is going to be the inverse tangent of EPY divided by EPX, which then works out to be 64.6 degrees. Okay, so this is the angle. Now, if we go back to what we did on Friday, it turns out that this angle is exactly the same as the angle we got when we were looking on the force of Q3. And again, the reason for that is, if we go back to our electric field, we know our electric field is equal to the force divided by the charge, which means that here we would take that force that we had before, divide by the charge of Q3, which means the angle doesn't change because Q3 was positive. And we can actually check the magnitude of the force, check the magnitude of the electric field by taking the magnitude of the force that we got before and dividing by Q3. So that would then give us that amount of force. Always okay? Let's do another one. So let's get rid of this one. So the next one says that two particles are fixed on the x-axis. The first one has a charge of 8q. The second one has a charge of -3q. And it wants separated by distance of L again. And we want to know at what point, other than infinitely far away, is the electric field equal to 0. So, good. So now what we have is what? Here's Q1. Here is then Q2. Again, these two are separated by a distance of L. Here is X. Here is Y. And again, what we want to know is where can we find a point where the electric field at that point is simply equal to 0. Good. So basically, to do this, we'll do exactly the same thing we did before. Let's write this into region 1, region 2, and region 3. And then look at each one. So we'll just do the same thing as before. So the question is, can I have a total electric field of 0 in region 1? So what do you think? So could we have a total electric field of 0 in region 1?
This is the same numbers as before, isn't it?
Yes, it is.
Okay, so we would already know, but the magnitudes for region 1 would be where the vectors would make that having a force, so it wouldn't be 0, so no.
So yeah, so now we're just taking that and dividing by Q3, so exactly. So the answer is still exactly the same. So if I was thinking about this point here, so again here, let's call that E1 would point in this direction. Again, E2 is going to point in this direction, but again, it's much smaller, so the total field is going to point in this direction, right? So EP would point this way. Again, same thing here. If I was looking at this point, I know the electric field E1 points this way. E2 points radially into TIM, so it points in this direction, which again means the total field would then point towards Q2. This would be EP. And again, somewhere out here, we know that E1 is going to point this way. E2 is going to point this way. But again, due to the increased distance between 1 and the point and the decreased distance between 2 and the point, then there is a location where these two can have exactly the same magnitude. So yeah, so as Katie said, this is exactly the same problem we did before. We already know the location, so let's go ahead and write it down again. So just seeing if you guys were paying attention. So that was good. Good. So let's do the same thing as before. Let's define x as the distance then between the origin and that location. So again, we want here that the total electric field is equal to 0, which is then going to be equal to E1 minus E2. The same reason, because E2 points in the negative x direction. So this tells me then that E1 must be equal to E2. So finally, we're going to get that k times q1 over the distance here, which is x squared, must be equal to k times q2, again, magnitude, divided by x minus L, quantity squared, same reason as before. Again, k's cancel as they did before. We're going to do the same thing as we did before, simply take a square root of both sides, and then solve. So by the same logic as before, this thing came square root of q1 times L divided by the square root of q1 minus the square root of the magnitude of q2. And this is our location. Using the same numbers as before, this is 2.58 times L. So same exact location as before. Nice. Good. Let's do one more example. So the final example then says, not that one, this one. So it says, in the figure below, there are 3 particles are fixed in place where Q1 and Q2 have the same amount of charge of E, and then Q3 has twice the amount of charge, so that's 2 times E, where again, E is the fundamental charge. So that's 1.602 times 10 to the minus 19 coulombs. A here is a distance of 6 micrometers, and it wants to know what are the magnitude and the direction of the net electric field at point P due to the particles. Okay. So good. So let's do that. So let's draw. All right. So here is my y-axis. Here's my x-axis. So y and x. So what it tells me is at the origin here, this is then Q3, where Q3 has twice of E, and then some distance along the y-axis, where it's a distance of A. MC. Q1 has a charge of E, and then the same distance along the x-axis is Q2, which also has a charge of E. And then what we're looking for is at the point P, where the P is this location here. So this is P. So basically imagine this is a square, so it's directly at the center of the square. Thank you. A. Okay. So I said, so this is basically making a square. This is at the center of the square. Okay, so it wants to know what is the total electric field at point P. So let's draw our electric field lines again. So what I know is that what? E1 is, or Q1 is positive, so that's going to create an electric field which points in this direction, so radially away from that point. So this is E1. E2 is also positive, or Q2 is also positive, so it's going to make E2 also point radially away from that point. Q3 is also positive, so that's going to create an electric field which points also radially away from that point, which then points in this direction. So this is E3. Okay. Now, there are 2 ways to do this problem. One is the brute force method, which is basically write everything out and then try to calculate and see what cancels. And then the other part is to first stop and think about it and see what cancels. So this problem has a lot of what we call symmetry. So typically when we do problems like this, the first thing we want to look for is symmetry. What does symmetry mean? So symmetry means that we're looking for where these things are geometrically the same and they have charges which are the same, right? Which basically means that if I was looking at this diagram, what can you tell me about E1 and E2? So what can you tell me about E1 and E2?
They're the same.
They would cancel each other out.
They would cancel each other out, that's right. Because they're the same distance away, right? This distance from here to here is the same as this distance from here to here. The charges are the same. And since they point in opposite directions, what I can see here is that this problem has symmetry, which means that this one cancels out this one. which means then that the electric field at point P is simply equal to the electric field from the third charge. That's it. Because symmetry dictates that E2 would cancel with E1, which means the vector sum of those two would be equal to 0. So without actually doing any calculations, what we want to do is see what would actually cancel. So this is what's called using symmetry. So good. So from here, then what we know is that what? Well, this guy, E3, is simply going to be K times Q3 divided by the distance R squared. And this is going to point in what? Are you guys familiar with unit vector notation? Have you seen that before? Okay. Sine of 45 degrees. Okay. So basically just meaning that what? This thing points off at a 45-degree angle, so that this angle here is 45 degrees. Okay. So the last question then is, well, what is R? Right? So R is this distance here. So this is R. So let's think about the triangle that we have here. So we have this. We know this is A. We know this is A, and this is the distance R. Right? So this is the distance that we want. So what we know here is that R is actually equal to half of this total distance here. Right? This distance across here is 2 times R. Well, Pythagoras Theorem tells us then that 2 times R is the same thing as the square root of 2 times A, right? Are we okay with that? So Pythagoras Theorem says that if I have this guy, so if this was A, this is A, then I would find this distance here would be the square root of A squared plus A squared, which is the same thing as the square root of 2A squared, which is the same thing as the square root of 2 times A. Okay? So this means that 2 times R then is equal to the square root of 2 times A, which means R then is equal to the square root of 2 divided by 2 times A. So finally this says then that I can write this as K times Q3 divided by square root of 2 divided by 2 times A squared, all then times sine of 45 degrees. Okay. Plug in my numbers. My daughter is protesting. This then works out to be 160.2 times sine of 45, because I didn't multiply that part out, newtons per Coulomb. There you go. So those would be our vector formulation of that. Okay, meaning that the magnitude of it is then just equal to 160.2 newtons per Coulomb. Okay. It's okay. So this is the electric field then from a point charge. So again, electric fields from point charges are then simply equal to K times the charge of the point charge divided by R squared. So this is the magnitude. What are you doing here? Yeah. Don't pull in that cord. Yeah. Can you say hi to everybody? Hi, everybody. So again, so this is my charge. So it just means that the electric field again points radially away in all directions. So once I know the point at which I'm talking about, that distance R, then this is the magnitude of the electric field from that point. Ta-da! And again, if I have a more than one charge, then the electric field at that point is then simply equal to the vector sum of all the electric fields at that point. All right, so we'll leave it there for now. So basically tomorrow we'll talk about the opposite, which is basically that, well, let's say now we know the electric field, but we want to know the force generated by that electric field. So this is all calculating the electric field, but now if I know the electric field at a point, how do I calculate the force? Okay. So we'll probably do a couple group assignments tomorrow as well. So be ready to talk to each other. But other than that, we'll pick up from there and we'll do the opposite. So instead of going from the force to the field, we'll now go from the field to the force. Do the opposite. Okay. So, everyone okay? So it's a little bit weird right now. We're talking about these things of fields, which have values at every location, have direction at every location. Again, your primary job right now is to try to come to terms with that. So start thinking about things in terms of fields. They have values at every location in space. They have vector directions and et cetera, because again, we're gonna be dealing with fields throughout the remainder of the semester. So don't think it's gonna go away with the electric field. It will stay, and then it's gonna come back again with the magnetic field. And then as we talked about at the beginning of the semester, light is electromagnetic radiation, which is an oscillating electric and magnetic field. So we have fields for the rest of the semester. So spend some time trying to come to terms with these fields, okay? Because they're not going to go away. Okay, so if there's no questions, everybody's doing okay, then I'll see everybody tomorrow. And yeah, have a good day. Bye.